Yeah, actually, we are a little behind, so maybe that's sure. Yeah, actually, we are 3 minutes behind. So, okay. Okay, good afternoon, everyone. It's our great pleasure to have Professor Ting He from Penn State to give a seminar today. So let me first briefly introduce Ting. Professor Ting He is an associate professor in the School of Electrical Engineering and Computer Science at Penn State. She received her PhD degree in electrical and computer engineering from Cornell. Her interest resides at the intersection of computer networking, programming, performance evaluation, and machine learning. Dr. He has served as an associate editor of IEEE Translation on Communication and IEEE ACM Translation on Networking. And she's a general co-chair of several major top-tier conferences. And she also has received multiple paper awards from IEEE Communication Society, ICDCS, Symmetrics, and ICOPS. So without further ado, let's welcome Professor.
Thank you so much, Kevin. And thank you everyone for being here. I was trying to come up with an interesting topic than just directly say the technical words. So I call this topic CT scan for your network. I'm Ting. So before I dive into the technical details, I have this icon that you put this cloud stands for the network that you want to monitor, and you throw it into this CT scan machine. We all know CT scan, right? Anybody know what the two letters CT stands for? CT.
Tomography.
Computed tomography, right? CT is computed tomography. So we know what CT is used for, right? It's used when you want to sort of look into a closed object like human head or chest, right? But you do not want to sort of slice the object open. That's the whole point. You want to keep it closed, but you still want to look inside without being intrusive in your measurements. And I will come back to this point. Since I figured out this is the first visit here. Oops, sorry. This is my first visit here. Okay, I have to use this. Okay. I will just use this one slide to quickly introduce me. This is me and 80% of my group. And we do two types of work at Penn State in the so-called network sciences research group. One type is more domain specific about the communication network itself. Examples being the topic of today, something called the network tomography. And I have also worked on a project which is about security in the context of software-defined networking. So these are about the networks. Another bunch of my topics is related to the application, so the workflow that you want to run over a network, but the focus is on optimization within the application itself. So either dealing with the network or dealing with the application on top. And today's content, oops, sorry. The delay. Today's topic is this first bullet here, network tomography. Okay. So as you can imagine, the reason that I call the talk CT scan for your network is because of the shared keyword tomography. What CT scan is trying to do is essentially you send penetrating waves, right, through ultrasound, etc., through this closed object that you want to monitor. And you don't do it just from one pass, you do it over many, many passes from the peripheral points outside this closed object. And you use multiple such end-to-end measurements to reverse engineer what could be the internal state of this black box object that could have generated this set of end-to-end measurements I've seen. It's essentially about solving an inverse problem. Network tomography, you can think of it as sort of the discrete counterpart of CT scan. It's about doing such a reverse engineering about the closed graph that represent a communication network. Now, it depends on what exactly you know about this network before you start the measurement. Network tomography can be divided into two separate branches with very different solution techniques. One branch So-called performance tomography is when you assume that you know the structure of this graph. You not only know the graph topology, you also know for each measurement, let's say from this point to this point, what's the sequence of links and nodes that I traverse in this known topology graph. The question is about the performance metrics, such as link loss rate, capacity, delay statistic, etc., on these internal links. We know that you can use link metrics to model node metric as well. So that's why it's called performance tomography. The other branch, which is the black box setting, is more challenging. That's what I want to talk about today. It's known as network topology tomography, or more commonly known as topology inference. So you are still measuring end-to-end between a set of vantage points on the peripheral of this target network. But before you start measurement, you assume no knowledge about internal of your network. So it's a black box network. I only know that I have these vantage points. What's the performance measurement? I have the loss, delay, etc., between pairs of vantage points. And I want to essentially jointly reconstruct the internal routing topology together with the metrics on the links of this inferred topology. That may sound like violating information processing inequalities, like you start with not knowing anything, and you magically hope to recover both the structure and the performance state of this black box network, right? So a natural question is that problem even hopeful? When is it ever solvable? So essentially, there is no magic in the word. The magic here, seemingly magic, that you can violate in the information processing inequality is whatever you do not directly measure, you make up by assumptions. So you use side information to make that up. Okay. So before I go to that, let's take a step back. When do we want to do this? And why can't we directly see the information about the internal state? Network tomography, the term originates about 20 years ago in late 90s and early 2000s. Some of us may remember that's the period of time where the academics become curious about what the internet looks like, right? There are multiple big projects, Rocket Fuel, etc., that's talking about let's map the internet mapping project. And of course, the system approach to map the internet is to look at the various protocol information. Let's look at the BGP routing table. Let's use dedicated measurement tools, traceroute and its extensions, etc., to directly measure the information pass by pass. However, if you look closely at what's required for those tools to work, they always require various extent of support from these internal nodes, the routers, in that case, inside the internet. Right? For example, for traceroute to work, we know that your routers need to be configured to respond to TTL expiration by sending back an ICML message to the source, right? But the routers may be configured not to respond to ICMP. For example, they are called, not ICML, sorry, ICMP. Those are called anonymous routers. And then there are actually larger scale measurement studies showing that in the current internet, the ratio of routers that are configured to be anonymous is increasing, as you can imagine, because for the routers to be exposed, there's security risk to it. All right. And a more classical approach is that from the administrator's perspective, you just run monitoring agents as individual network nodes. And then you pull APIs from those monitoring agents through some control plane protocols. This is, for example, how we traditionally manage an enterprise network as SNMP, how we traditionally manage as software-defined network, such as OpenFlow. But if you look across these different approaches, one thing they share in common is that they require what's being monitored, the internal nodes of this target network, to agree to be monitored. You need to open up sort of control plane ports for you to get that information to begin with. Tomography takes a very, very different approach. It's essentially trying to deduce this control plane information, network routing, topology, performance state, etc., from data plane measurements. And once we get this information, we can use it as we normally would in a variety of network management functions, such as route optimization, service placement, client server association, etc. All this can be done either at network layer or above. So now let's.
So Ping, can I ask you a question?
Sure.
So I guess I'm trying to sort of think like if, like right now, I'm assuming tomography is very useful, let's say in the internet, right? In the sense that because we have so many different networks that are combined, therefore, it's very hard for one provider or one user to sort of understand, the network configuration itself, right? But then the internet protocols in some sense, like routing, etc., are already hard coded, right? They're already in the system, right? So even if we were to learn the topology, is there some way in which we can actually use it?
Question is, so what, right? Why do I want to know this
Right.
information if that's not a controllable network?
Exactly.
I'm going to reach that point to the second half of my talk through an example about a very typical function that's normally done by the owner of the network self, routing. But you can actually do routing from the application perspective, which is overlay routing. Right? So that's a very good point. In other words, you can think of tomography as sort of an application layer technique to mimic network layer functionality, network layer control plane functionality. But you can do so through an overlay, and you can implement it in application layer without explicit cooperation from the network provider. So coming back, that seems again, the hope is good, but what makes the problem solvable? So dating back to early 2000, this problem was considered solvable initially because of a humble observation like this. Consider a toy example, right? I monitor these two paths from source to two different destinations. And this is a logical contraction of my routing topology. So I have a multi-hop path to destination 2. At some point, they're going to branch. That's what you're going to get in the current internet because of the destination-based forwarding. This is a two-leaf tree, very, very simple, right? But what can I deduce about this two-leaf tree if I take end-to-end performance measurements on these two paths? So the trick is that if you can do multicast, in this case, bycast. Bycast is for the source to send a single packet until it reaches this branching point, which will then duplicate packet and send it separately to each of the destinations. So you only have, for each probe, you only have one packet traverse each of the links in this routing tree. What you get because of the multicast is that if you look at, for example, let's look at end-to-end loss measurements, right? If I use X sub P to denote the indicator of success for path P, then this path success probability under the spatial independence assumption will be equal to the product of the link success probabilities, right? So on this path, I can effectively have a consistent estimate of alpha 1 multiply alpha 2, and on this path, I can effectively estimate alpha 1 times alpha 3. In addition, because it's a multicast probe, if I jointly look at the joint success probability on both paths, so what's the fraction of probes that can successfully be received at both destination 1 and destination 2? That gives me what that probability is equal to the product of alpha 1, alpha 2, and alpha 3, right? So that's a multiplicative relationship, but we can easily convert that to a linear relationship by taking log, right? For convenience, I'm going to take a minus log, which gives the so-called loss-based metric. And that's a non-negative metric, which is additive across hops. And if you stack the measurements together, these marginal success probability and joint success probability is going to give you such a linear system, which is full rank. So that means you can actually invert the system to uniquely infer the additive metric on each of these three logical links, right? So why does it tell us something about the topology? Note that if the link, this alpha 1 shared link, has non-zero metric, means that it has non-zero loss, right? Then we know that there must be at least one physical link, maybe multiple, but at least one that's shared by pass 1 and pass 2, right? Vice versa, under the assumption that every link introduces some non-trivial loss, then the fact that if you have a zero metric on the shared link means that you actually do not have this topology. You have no link sharing. You have a 2-link tree instead of 3-link tree as shown here. So you can deduce a logical equivalence of the actual routing topology together with the performance metrics on the logical links. You cannot say for sure that, okay, this is just traversing one IP hop that you don't know for sure. You may have a sequence of hops, but you know the logical equivalence of the link as well as its performance. Okay, so this is a twin example, of course. And the existing work realized that this assumption that you can use correlated measurements obtained through multicast probes to deduce tree-like topology actually can be extended to an arbitrary sized tree. So always rooted at probing source, and you can have many, many leaves corresponding to each of the multicast destinations. It's known that you can consistently estimate the corresponding canonical tree with link contractions on each of the tree branch. So that is a known result. And now let's see a broader look, looking back at history about what has been done and where are we right now. So as I said, this whole idea rooted back 20 years ago for this observation that if you can do multicast probing, you can generate equivalent canonical trees for a single probing source, right? And then there are multiple extensions immediately following that. One is we know that multicast is not always enabled in IP networks because of security impact. Can we do unicast-based counterpart? And the idea is to basically, instead of sending a real multicast to multiple destinations, I'm going to send a train of back-to-back closely spaced unicast measurements with the hope that closely spaced packets experience almost the same performance as shared link, if any. So you can mimic multicast performance measurements. And then if you sort of try to do this probing and inference rooted at multiple probing sources, then you can try to combine those trees to give you sort of n by n topology. That's the so-called multi-source topology inference. Okay, now where are we? We started inception on this problem about 6 years ago, around 2018, 2019, because I was working on that gray box model, topology, the performance tomography, then got attracted to this more challenging black box model. At the time, actually, there's a wave of intensive interest from research community on newer paradigms of networking, including software-defined networking, SDN, network function virtualization, right? You place these intermediate network functions that the flow needs to traverse in specific order before reaching the destination. So both the waypoints as well as the generalized forwarding under SDN cause a disruptive change in the ground truth when you do topology inference, that the routing for each source is no longer necessarily tree-based, no longer form you a tree. So that's the inception point. And we're trying to revisit basically these problems under this new networking context when you have more complicated solution space, right? To what extent we can still solve the problem. And to organize a sort of bird's eye view of my understanding of the landscape of what we know so far, I will beam existing results sort of along two different dimensions. The x-axis here is the basically complexity of the ground truth topology in terms of the flexibility of routing. Right. The most traditional IP-based network, they do destination-based forwarding. So the topology is always a tree for each source and a union of trees for multi-source topology. We are always talking about routing topology. And if we deviate from that, we introduce, let's say, service chains. then the network functions on the service chain are basically waypoints, traffic flow must traverse. And the more general case is, of course, combination of SDN and NFV, which gives you almost arbitrary routing topology, right? So when your solution space get more and more complex to what extent you can still solve the problem. The y-axis is in terms of how much you measure, not necessarily how much you measure, but how much you collect active measurements. So I said that one way to mimic this multicast induced correlated measurements is to do controlled unicast. I have to carefully space my unicast probes to the target path so that they achieve sufficiently high correlation on shared links, if any, right? But the active probing is going to cause a high traffic overhead, right? That's part of the measurement overhead. Can we probe less? That's the question. The most extreme case is that there's no active probe, and we only passively snip the end-to-end performance measurements on the data packets, in which case you have no control on what's the correlation, what type of correlation you have across paths, right? And we have some scattered results in these blue beans. These white beans are basically, to my knowledge, completely unknown, completely uninvestigated as of now. And most of the existing solutions in the space of topology inference is in this bin, when you can probe all the paths you care about. There's no overhead concern. And you always assume that the set of paths starting from every probing source or leading to every probing destination, they each form a tree. The overall topology is a union of tree. Yes, please.
Yeah, so quick question is, I'm not sure about what's the performance metric for this topology inference, but would there be any trade-off between these, how many paths you can probe and the performance? So intuitively, like you can probe more paths, then you will have more information.
Right. So that's not a question about how you get to the answer. That's a question about how the accuracy of the answer depending on the question.
Exactly, yes.
Right. What's the target? How big of a routing topology you're
Yes.
trying to infer? That's a great question. That's a scalability question.
Okay.
There is a significant, to my knowledge, depending on how much limitation, how much assumption along this axis you're willing to make about the routing in your target network. For this category, the scalability is better. Trees have special features I will show. If you go, for example, to this extent, scalability is still, I would say, it's an ongoing research topic. We have some solution, but you are going to see notable degradation in accuracy when you jointly consider more and more paths.
Okay.
Right. I want to mention that when you talk about topology inference, the target, the inferable topology is always the routing topology, because what's not traversed by your measurement packets are not visible to you. That's, I guess that's intuitive, right? So it's always about routing topology inference. What I'm going to do is that I don't have enough time, so I will just deep dive into positive and negative results in this one combination, where you throw away any restrictions about what kind of topology you have in the ground truth, arbitrary routing, completely arbitrary. And let's just ask a fundamental question. Without any of this sort of side information, right? I don't know anything about what kind of graph I have, just purely based on my performance measurements end to end. Let's say you can probe any way you want. What exactly is the information I can uniquely determine? We call that identifiability, right? What's the identifiable information? And then we can ask how useful is that information in terms of reconstructing the routing topology. Okay. So this work is motivated when we're studying the counterpart of topology inference-based network monitoring in the context of SDN combined with NFV network. So you have service chains that you need to traverse. And you also have generalized forwarding, which can cause weird routing topologies. So even if I have a single source, single destination, but I may have multiple flows, right? Data flow or probing flows. And I can use SDN rules to set up a non-tree based routing path. I may have a path going like this. I may have a path going like that, right? Because I can use general forwarding, I can probe all those paths. And let's say the union of the paths you can probe gives you the ground truth routing topology. All right, so we cannot assume the ground truth must be a tree, but we can still collect the end-to-end measurement. Let's say you measure the end-to-end losses or end-to-end delays. I'm going to use loss as an example, but delay also works. So let's assume that we measure the length of each link by the so-called loss-based metric, which is minus log of the link success probability. So loss-based metric, and we collect end-to-end losses as our raw observations. What information can we uniquely deduce about this topology? To this end, let me first show you a negative result. So we have accumulated over a decade of algorithm together with theory when you have tree-based networks. The first question coming to our mind is, it doesn't necessarily mean that because you lose the tree-based routing assumption, you have to throw away all your existing results. Can we just reapply sort of old hammer on this new nail and still get something that's meaningful? Right? You can do a performance analysis first. However, I will show you a negative result.
Sorry, can I ask another question? So, in your model, these alpha i's are independent.
That is correct. That's the spatial independence assumption is always there. That's
I see.
inherited from the existing topology inference works.
Right.
Right.
I
They
guess
also
when I'm looking at something like, let's say, the internet, again, with, where mostly TCP is being used on systems and congestion is probably quite correlated unless most flows are single hop flows. I guess if most flows are single hop flows, then maybe one could argue that independence might still hold. But is
Right.
this something where
Right.
you've seen it validated in any way?
We haven't done this internet measurement
Mhm.
study, to your end, to answer your question. But intuitively, it's not necessarily that there's no multi-hop background traffic. What matters is the dominant background traffic going to across multiple hops of the routing topology of interest or not. For example, if you are monitoring at the peripheral a particular autonomous system, let's say in a core, right? And a core network is a transit network. It's going to be traversed by traffic in all directions, right? Then I guess intuitively you can argue, we didn't do that measurement study, but intuitively you can argue that there's hope for you to have sufficiently disjoint set of flows traversing each of these hops. And by the way, these are not these are not physical IP links. These are sort of logical links between branching closest branching joining points. Right.
I guess.
If that is
yeah.
the case, then we can still hope for spatial independence to be a good approximation. But of course, that's an approximation.
Yeah, no, I'm thinking about it, I think the spatial approximation might be okay. Because of the mixing, right, that's typically happening. I guess temporal might be a little more problem if you need temporal independence. Do you need temporal independence?
No, actually temporal, we need two things because we're mimicking multicast, right? Suppose you're doing unit-based mimicking. Then first of all, for the probes, unicast probes mimicking the same multicast, you want those probes to be as correlated as possible for the shared links.
I see.
And that is because of queuing. For wired network, that is because of queuing. Then you have to design your probes to sort of be sufficiently separated so that you have the mixing effect. You don't want the nearby probes to be perfectly correlated, otherwise your measurements do not give you new information. Right. Right. So for that, there are internet studies that say something like if you space your probes by at least hundreds of milliseconds, then they will be like roughly empirically independent. Right. There's a trade-off. Okay, so I'm going to show a toy example actually to motivate the gist. The conclusion is that unfortunately no. And let's see a toy example. So the toy example being this again is a non-tree routing topology formed by just the three paths shown by these colors, right? And what are these numbers? These numbers means those loss-based link metric. And link metric of 0 means that this is a lossless link because it's minus log of link success probability, right? Let's say this is the ground truth. So, and you have sent as many probes as you want, right, on each pair of paths, so that you can perfectly estimate the path success rate and the joint success rate on each pair of paths, right, asymptotic regime. Now, even if you ignore the estimation errors on the path metrics, you would still get a dilemma like this. This is basically the ground truth, path length, and shared path length. Shared path length means that it's basically minus log of the joint success probability on this path manipulated with other individual link measurements. It corresponds to the summation of the links shared by each pair of paths. For example, P1, P2, this is P1, P2, they share these two links, and their ground truth shared path length would be 1 plus 3, right? And similarly with path length. So you get this ground truth asymptotically. But my claim is that you will not be able to find a single root 3-leaf tree that perfectly reconstruct all these path metrics simultaneously. You cannot. The reason is that if you look closer, for any 3-leaf tree, let's say for this tree, two of the leaves are going to branch away from the third leaf, right, at some point. Now, these two, which are siblings, let's say P1, P2, they are going to have the same shared portion with the third path. And therefore, at least 2 out of the 3 shared path lengths must be equal, which already deviate from what you measure because your ground truth is not a tree. What I'm trying to say is that even if you ignore the measurement, the estimation error, if you limit your solution space to trees as is traditionally assumed in the literature, once your ground truth topology deviates from tree-based routing, you cannot even guarantee a feasible solution, meaning it's a weighted graph you reconstruct that simultaneously match all the path metrics that you have inferred. Okay. So the conclusion is that no, you cannot just reuse the existing algorithm. You need a new algorithm. We need a new solution. So that's a negative result. Now let me show you a positive result, not immediately about the topology, but about something that's even more fundamental, I argue. So the question is, now we have a complete black box network. We have no idea about how routing is done inside the network. We have end-to-end measurements. Exactly what information about internal state of the network can be uniquely determined from my end-to-end measurements. Okay. To explain that, I need to introduce a definition, a notion that we call category. For a category, let's say gamma F is a subset of the links in the target network you're trying to measure, okay? And this, by definition, is the set of links that's traversed by and only by the path indexed in F. For example, let's say this is, again, 1, 2, 3, a three-path routing topology. Link E5 and E10 here, because they're traversed by and only by path 1. They both belong to category 1. And link E9 here, because it's shared by path 1 and path 3, and none of the other paths, it belongs to category 1, 3. So that's what I mean. Basically, we are partitioning the set of links in this unknown black box network according to how they are traversed by the measurement path. Links in the same partition, we call them one category. Okay, so what's the use of this definition? Now, the claim is that if you look at the summation of these additive metrics, let's say loss-based metric, of all the links in the same category, let's call it category weights. I claim the category weights are the finest granularity information that can actually be identified from your end-to-end measurements. Specifically, according to the definition of categories, completely based on how the links are traversed by measurement paths, right? We have this deterministic linear relationship between what we can infer from end-to-end measurements. Each will correspond to each is a function of the success probabilities on a subset of the measurement paths, right? These probability under the spatial independence assumption is equal to the product of all the link success probabilities for the links in the multicast tree, right? So after you take the minus log, you got this additive metric, let's call it cast weight. By definition, this cast weight has a fixed linear relationship with the category weights. The equation may look non-intuitive, but it's actually saying something that's quite simple. All I'm saying is that let's look at, for example, the cast weight for pass 1 and pass 2. It corresponds to the joint success probability on pass 1 and 2, right? So it depends on the success probability on all the links traversed by either of these passes, union of pass 1 and 2. And that total weight is equal to the summation of all the link weights for links traversed by pass 1 only, all the link weights traversed by pass 2 only, and all the link weights traversed by either pass 1 or pass 2 and one of some of the other paths, right? Because it's a union. And I can do the summation because by definition, the links in different categories, they must be disjoint. These are disjoint sets, and therefore I can just add up the additive metric. The next thing about the formulating this linear relationship is that it's completely agnostic of your routing topology. The true routing topology can be arbitrary, and this relationship is always true. The linear system looks identical. What the actual topology determines is the value of those category weights. For example, if the topology is such that there's no link traversed by and only by pass 1 and 2, but not pass 3, that this weight will be 0, right? This weight will be 0. So different ground truths will only affect the value, but this linear system you can always write down just by definition. It's topology of the state. Yes.
Yeah, but so in that case, though, the number of paths that you're considering, the size of the problem grows exponentially.
Exponentially, exactly.
Is there? Yeah, I mean that is quite clear. But is there a specific relationship between the number of links that you would like to get out of this, or the estimation of that, and the number of paths that you want to try out?
Very, very, very good question. Very good question. So first of all, this is going to be a huge system. It's a linear system, but it's going to have exactly how many? 2 to the, if you measure n paths, right? That's your target topology. It's going to have 2 to the n-1 equations and 2 to the n-1 unknown variables. I didn't show that. Additionally, we have proved that this linear system is always correct. So you can invert it in theory, but you have a scalability problem with the number of paths. So basically the size of the topology. And your second question is an intriguing question. So the truth is that because this network only traverses so many ground truth links in the actual communication network, right? That cannot be a huge number. That cannot be a huge number. And if you look additionally at the definition of categories, the links in different categories must be disjoint. That means the number of categories which are non-empty for a given routing topology, that cannot be a large number. That number must, to be precise, must be no more than upper bounded by the number of links in this target network, right? So you actually have a exponentially large linear system, but you know already that most of these candidate variables will be 0. Only a sort of linear size subset will be non-zero. However, which linear subset is non-zero is topology dependent. So that's the trick. That's the tricky part in solving this problem. I'm going to show a way to sort of incrementally solve this problem with polynomial complexity guarantee later. So that's basically, in theory, it tells you, oh, in addition, Because this linear relationship is already fixed, it's agnostic to the topology. You notice that once I specify all the category weights, I already specify the essentially the distribution of my end-to-end performance measurements. It's going to be agnostic, independent, conditionally independent of how many links I have in each category and how they are located, right? So in other words, it basically combined with this zero means that if you only look at end-to-end performance measurements in terms of these kind of additive metrics, the category weights are the finest granularity information that you can uniquely identify in the asymptotic region, but that's what you can uniquely identify, not actually the topology. It's not the topology, it's the category weights. It's the finest granularity because of the conditional independence of the actual topology. Okay, so that seems to be a little contradictory with all those existing papers that claim that for tree-based routing, they can actually infer this logical tree topology with accuracy guarantee. So what's going on? And that's because of the following. For tree topologies, specifically is this so-called canonical tree. You can track the sequence of links on the same branch. There is one-one correspondence between the category, non-empty categories, and the logical topology. For example, if I again measure 3 paths, right, and you solve that linear system, let's say, and you get the following conclusion that if you threshold on the category matrix, you detect these subset of categories are non-empty. And then I claim that this is the unique canonical tree that are consistent with this set of non-empty categories. So for tree topologies, knowing the category is equivalent in determining the logical topology. But the same cannot be said once you get rid of the tree assumption if you are dealing with an arbitrary routing topology. As a counter example, actually we have an algorithm which always works. So you give me any subset of the categories detected as being non-empty, I can always algorithmically sort of construct a dense clique-looking topology that represent exactly those subset of non-empty categories, sort of like a clique embedding algorithm. I'm not saying this is a good way to infer topology. This is more like a counter example that knowing category information itself doesn't directly give you a unique solution to the topology. So that is a negative result. That's a negative result. And I'm going to skip this, just to give you an intuition about what it leads to. For example, this is your ground truth topology, where these green nodes represent NFVs that you specify how you want to traverse them. And these are the destinations. You have a single source, right? For existing topology inference algorithm, because it's a single source problem, you always try to reconstruct a tree. This is something called routing neighbor joining algorithm, which has accuracy guaranteed if the ground truth is truly a tree. And obviously, these two topologies look by no means similar to each other. Not only that, if you look at the path lengths and shared path lengths, they are going to be significantly different from what you actually measure, because that's the limitation of your solution space. That's sort of a statistical evaluation of the counterexample we have seen. So you need to look at more general graphs if your ground truth is more complex. But if you just use the categories, by the way, this is already ignoring the estimation error. I'm already giving the perfect information about category weights. Then you can still construct such a feasible solution by clique embedding, which again, by no means looks similar to the ground truth. One possible direction is to throw in additional prior knowledge. For example, if this is truly an NFV network, sometimes by looking at the symmetrics of the traffic flows, we can deduce information about the sequence of network functions that it needs to traverse. With the service chain information, you can do better. This is, again, a best effort solution. You can see that compared with the ground truth, it seems to better reconstruct the structure. But still, the two graphs are not exactly the same, and you have no guarantee on how close you are mimicking the ground truth. Fundamentally, it's because once you get rid of the tree assumption, your solution space is so large that you don't have unique solution. So if I stop here, it sounds like once we need a tree assumption, right? Basically, we can only do topology inference if you have a traditional destination-based forwarding network. Otherwise, you don't have a unique solution. But I want to move a little bit away from the original goal of reconstructing the routing topology. So the question is, what do we do with the topology ultimately? That's what we care. Not about just for fun, I want to look at the graph, right? So it turns out that the information, remember the categories. The category information we said we can uniquely identify turns out to be very useful for something that the application layer cares about. I'm going to show a concrete example in the context of overlay routing. So overlay routing is just one of the overlay-based value-adding services that we normally want to run because the IP-based core network is just too simplistic, right? For example, you may want to have a set of CDN nodes, right, on the peripheral of the internet on multiple sites. And if you look at the CDN gateway routers as overlay nodes, you can sort of steer your traffic through tunnels among these overlay nodes in order to optimize your end-to-end routing performance, right? And such services are indeed being commercialized. For example, there is a recent concept, which is sort of an incremental way to deploy software-defined networking called software-defined wide area network, SD-WAN. That's proposed both from the provider side, such as AT&T, and sort of a device vendor side, such as Cisco, right? And these edge routers can be viewed as overlay nodes that you can sort of form multi-hop paths among. Okay, so how is that related to topology inference? Let me show you to an example again. Okay, so let's say I'm the operator of this overlay network. From my perspective, I actually have a flat network like that. And if I just optimize the routing of flow demand, let's say I have some flow from A that wants to go to E, and the flow that enter in B and wants to go to D, right, between my overlay routers. If I just directly optimize my routing within the overlay topology itself, bad things can happen. Why? Because these seemingly independent overlay links, which are actually something like IPsec tunnels, are implemented by multi-hop paths through the underlying communication network, such as ISP network. And these seemingly independent tunnels can actually share links within the underlay that's agnostic to the overlay provider. And that can cause problem. For example, maybe if you want to send two large flows, marginally you can send flow 1 without congestion, you can send flow 2 without congestion, but not concurrently flow 1 and flow 2. And that is because this link is shared. This link is shared. So that means we have such cases where we need to be aware of the mapping between panels and the actual links in my underlay. I need to know what's going on inside the underlay. But on the other hand, the providers of overlay could be like a CDN provider, VPN provider, or just a cloud provider who wants to use Cisco vEdge routers to connect my data centers. Is typically not on the same side as a provider of the underlay, but which would be public ISPs. So you cannot assume you have cooperation or control plane information directly from the underlay provider. The research question is, then can we still do something that's sort of underlay aware without direct support, control plane support from the underlay? So that naturally link back to the topology inference problem, because what you need is basically topology information, routing topology information. Of course, if you have perfect topology inference solution, then you can basically run a constrained routing optimization in the actual underlay network, right? But we know that topology inference by itself is far from 100% reliably solve the problem. And that's actually sort of overshooting of information. So to be concrete, let's look at a typical objective of routing optimization. This is the typical shortest path routing problem. Specific is least cost path routing problem. Let's say I have a certain cost in using each tunnel, and I want to sort of schedule my overlay level flow demands among overlay nodes only, subject to the typical, let's say, flow conservation constraint. This is a single pass constraint and link capacity constraint. But your link capacity constraint cannot be independently imposed on overlay links because they are tunnels. They're just logical links. They do not come with capacity constraint. The links with capacity constraints are the underlay communication links. So you can easily reformulate that by counting the amount of overlay traffic load you impose onto each tunnel and some overlay tunnels traversing each link in the underlay, right? So that's the actual routing problem. The problem, however, is that to formulate this optimization, you need to know very detailed information about underlay. Specifically, this information about how the tunnels are routed through the underlay, that's effectively asking about the routing topology of the underlay. That's topology inference. And also you need to know the underlay link capacities. That's also right? What I'm going to show you sort of it's a way to bypass the requirement of such detailed information. And I'm going to link back to the concept of categories. I will reintroduce the category definition, except that I add this parenthesis E. It means that this is the subset of links traversed by the subset of tunnels F out of all the currently considered tunnel E. I put E into parentheses explicitly because later on I'm going to vary what set of tunnels I consider. All right. Okay, so it's the same definition as before, category weights, and I know that those category weights are uniquely identifiable if I can probe. Okay, but the key observation here, we leverage this prior knowledge, is because I claim that the knowledge of categories will be sufficient for our goal of congestion-free overlay routing. So why is that? Okay. At a very high level, you can imagine you are only steering traffic between overlay nodes at the granularity of tunnels, at the granularity of overlay links, right? Because you're doing so from the overlay provider's perspective. You are not going to steer traffic and the granularity of underlay links. As a result, all the links in the same category, which are by definition traversed by exactly the same set of tunnels, they must receive the same traffic load from the overlay. They must receive the same traffic load because they are traversed by the same set of tunnels. Right? Therefore, if you look at all those link by link capacity constraints, you will be able to group them because the left-hand side is the total traffic load imposed by the overlay must be identical for all the links belonging to the same category. And therefore, it suffices to have one constraint for each category, where on the right-hand side, I impose the minimum link capacity for the links within the category. Let's call it the category capacity. So it suffices to have per category capacity constraint. And that's sufficient for congestion-free overlay routing. Now, what's better now? What becomes better is that instead of requiring fine-grained information on the exact routing topology, we only require information about which subset of tunnels share link in the underlay. I only need to know which categories are non-empty. And also on this side, instead of knowing individual link capacities, we only need to know the minimum link capacity per category. It becomes sort of a coarser grained category level information that I need. I know that I only have a few minutes, so I'm going to just talk about a key challenge that we need to solve So we know that we need to know these two pieces of information. We need to know the minimum link capacity per category. We also need to know the set of categories which are non-empty, because we know that out of the exponentially many in a given instance, only a linear subset will be non-empty, right? So this, as you can imagine, is a harder problem. How do I figure out the non-empty variables in the exponentially large linear system without solving the linear system to begin with? Okay. So the observation is that, skip. The observation is dynamic programming. So because we know that in theory, the problem is solvable, the difficulty is the scale, right? If I only consider a few tunnels, then I can solve the problem. By the way, one tunnel here corresponds to one measurement pass. Then I can solve the problem. So the question is, if I already solved the problem by considering a small subset of the tunnels, can I sort of reuse that information and refine it to get a solution for a bigger subset of the tunnels? Dynamic programming. And the gist comes back to the definition of category. So category is a partition of the link space based on how they are traversed by the paths. Here, the paths are tunnels, right? For example, if initially I only consider these two tunnels, A to D, B to E, then these two underlay links, they are going to belong to the same category, right? Because they're traversed by both of the considered tunnels. However, when I consider a new tunnel, which let's say go on this path and the bypass go to D, then these two links now are separated. In other words, this previous category, because of consideration of a new tunnel, is now refined into two new categories. This is traversed by all three tunnels, and this link is only traversed by two out of the three tunnels. You have this refinement effect. This refinement effect will partition each of the previously detected non-empty category into at most two new non-empty categories. So you're at most doubling the number of non-empty categories in each iteration by considering one more tunnel. That by itself seems to be still bad exponentially growth, but that's in the, we can combine that with the observation that because we know the number of truly non-empty categories must be upper bounded by the number of links in the underlay, and that cannot be such a large number, right? So these two observations combined together gave us a dynamic programming algorithm like this. I will skip the detail of the algorithm. This is essentially by iteratively solving a sequence of linear systems. Each linear system has a size that's linear in the size of the underlay, and the number of iterations is linear in the size of the overlay because you are adding one tunnel at a time. Right? So overall, that gives you polynomial complexity algorithm to infer all the category weights, which can then be compared to threshold to detect non-empty categories. Okay, I'm going to, in the interest of time.
So when you say
Yes.
the linear system is size is linear in the underlay network size, do you mean number of network nodes, number of network? What
Links,
links?
yeah,
Links.
using a sort of a graph theoretical term, some people say the size of a graph is the number of
The
links,
links.
and the order of the graph is the number of.
So that's interesting. So basically, so no matter what the connectivity of that network is, the underlay network,
Connectivity and the routing.
you still have it linear in terms of the in terms of the number of links.
Linear in terms of number of the
Link.
links in the underlay
Underlay.
network, because by definitions, no link can simultaneously belong to two categories. They must be disjoint. So that gives you an upper bound essentially on the
Okay.
number of variables which actually have non-zero value. Upper bound on the number.
So
of
that's how you get around the exponential growth.
That's how you get around, right? You basically gradually build up, and you know it has to be sparse. It's doubling, but most of the double variables, they are going to have zero. In theory, they're going to have zero metrics. In reality, they will have some small absolute metrics because you don't have perfect input,
Right.
right? You still estimate the path metric. That's the problematic part. So let me jump to the problematic part. There's a way, by the way, to infer the effective capacity on each category. So I'm going to jump forward. That's an easier branch. Okay, so we have this category information inferred. Now let's look at how that works. We did actually, I think, relatively honest simulation is packet level simulation in S3 with all those routing and buffering of packets, etc. Simulated, and we also inject background traffic. All right. So by the way, the background traffic we inject are independent across links. I have to confess that. Okay, let's first look at the most difficult part of the problem, which is the using dynamic programming to detect non-empty categories. As you can see, these are simulated based on 4 real ISP topologies. These are not huge networks. I would say largest has about 100 nodes and hundreds of links, which is the GTSE. The others are smaller. You have a huge number of categories which are empty. We only have 10 overlay nodes here. So that gives you 10 times 10 minus 1, 90 directed paths, right? For tunnels, and 2 to that number. That's the number of candidate categories. Most of them are empty because you only have so few non-empty categories. Okay, so that's just a empirical feeling of what I mean. And in terms of the number of false alarms and misses, false alarm means you detect an empty category as non-empty. Miss means that you detect a non-empty category as empty, right? We see that in terms of number of false alarms, we intentionally make it big by lowering the threshold on the category weights. But the ratio, the false alarm rate is very, very low because you have a huge number of empty categories. But in terms of number of misses, we can see that you can miss a substantial subset of the real non-empty categories. That looks bad. In the meanwhile, we have actually pretty good accuracy in terms of estimating the effective capacity. This is by piggybacking on existing single pass residual capacity estimation method. So I'm going to skip through that. Okay, now that looks bad, but the question is, what's the end performance in terms of optimized overlay routing, right? So this is what we probably care about. This is the actual perceived end-to-end relative delay. It's normalized by the delay you could got with perfect knowledge about underlay. Okay, so you can view that as a slowdown. And you can see that this purple bar is it's still beyond the state of the art, is as if you optimize the routing by looking at the overlay topology and the marginal capacity on the tunnels as a flat network. If you just do underlay agnostic route optimization within the overlay, treating the tunnels as independent, really independent links, this is the actual delay you get because of the congestion through the shared links. And once you introduce some awareness of the link sharing within the underlay, you get performance improvement, actually quite notably. This is surprisingly a state of the art, which is 16 years old. It's a 2008 paper by Bob Transgroup from U Toronto. And they did something called LCC. Basically, it's using existing shared bottleneck detection method to detect a subset of the link sharing to bypass to the same destination. Because they are not targeting at all the link sharing information, you have some reduction, but doesn't capture all the shared links. And this is the vanilla version of the proposed algorithm, that dynamic programming algorithm. You can see that although we have quite substantial miss rate, the result still gives you big performance improvement compared to the state of the art. And we did have a deep dive. The reason is that just because we missed the whole category doesn't mean we don't infer anything that helps to lower the congestion. You may miss there's a link belonging to category, let's say 1, 2, 3, but you may actually detect there's a link shared by pass 1 and 2, and a link shared by pass 2 and 3. You may detect this subset, which can still help you to lower your rate and minimize reduce the congestion. Okay, so the conclusion is that although we see from the absolute detection results, the inference part still has a large room of improvement. The result already shows a promising improvement, at least from the perspective of routing large flows among overlay nodes. Okay, so what essentially we have seen is an application layer technique to estimate the capacity region between scattered nodes on the capacity limited communication network. And once you got the capacity region, you can do a number of communication optimizations from the application perspective. For example, for CDN, you can use that information for client server matching. You can use that information even for content placement, right, among the caches in the CDN. For example, link to AI, if you want to do, let's say, large-scale distributed learning, and you want to exchange a lot of intermediate data, big models between the learning agents which run on top of a multi-hop communication network as underlay, then you sort of have overlay-based learning problem where awareness through this kind of inference technique about how the routing paths between agents share links in the underlay and the capacity of the shared links could help you to significantly improve your, at least the communication cost. So we're actually actively investigating the later direction, and I'm happy to talk more in person. Thank you.
Thank you very much. Questions? Actually, I have one quick question. So in the second piece, when you do this overlay routing with also using this like a better term, this kind of tomography. So is that routing problem solved jointly, or you do the tomography first and then you do the routing second?
Yeah, that's a great question. So far is a stonepipe solution. The first shot to do sort of we assume the ground truth is stationary. So you first solve your inference problem, then you solve your routing optimization problem, then you use it. I think what you mentioned is how do you keep up with the dynamics of the networks, the routing state and the link receiver capacity
Well, another
itself.
question, can we do this problem jointly? So maybe that would give you an even better solution. I'm not sure.
Jointly, you are talking about like online learning?
So it seems to me
type of,
you have a routing formulation, right? And some of the summation depends on the tomography you're doing. So yeah, if you treat that summation as another maybe like a bi-level optimization or something like that. So basically the whole problem if formulated this routing is formulated in a joint fashion. You do tomography and routing in a more cohesive.
Okay. Are you talking about how I got those measurements? Can I use my routing to get the measurements for the tomography problem?
Right.
That's a good point. However, a tricky part of that is because if you remember, we want to mimic multicast. For mimicking multicast, I think it's realistic to assume that you have to send a probe package, not data package. Because I don't know, maybe machine learning is different. Maybe you need a concurrent communication, but for other, if you are supporting independent TCP flows, you cannot control one application layer generate a data packet, right? So you cannot sort of perfectly control when you send out those packets. But to mimic multicast, you need to make sure the batches, the batch of probes meant to mimic the same multicast they are closely spaced. Thank you so much. Thank you so much.
Okay. Yeah, maybe that's the
Thank you.
Other questions?
Yes, please.
So when you were presenting your experiments, you mentioned that your third data set was more difficult than the other three.
The network topology data set.
Yeah. And so then for when you kind of showed the performance of the various methods, it seemed like there was less difference between the methods for that more complicated network.
The third network is not more complicated, it's just purely larger in terms of nodes and links. Are you talking about why the sort of the amount of improvement is less for the third network? It's not necessarily just the size. the size is kind of like directly linked to inference error. So that might be one of the explanations. But another is because of the topology for the third network. It's a real ISP network, GTSC. It happens so that you have this sort of dangling nodes on the peripheral of the network. Because we want to be realistic, we intentionally place those overlay nodes at the lowest degree nodes. And they have this thin access link, if you will, leading to the overlay that cannot be bypassed because that's the only way you connect to the rest of the network. So that basically leaves you less room for improvement. If you look at how overlay can help you, you need a way to bypass the hotspot, right? If there's only one way to go and that link is the hotspot, then basically nobody can help. Right.
Makes sense.
So,
Thank you.
so there are restrictions in terms of when you can achieve improvement. Right. Thank you.
I have a quick clarification question is that I'm thinking about the online offline optimization. So could you go back to page 23? Yeah.
There is a delay.
No problem. Yeah, I'm just thinking of
Yeah. Yeah, go ahead.
23, yeah. The index T is the index for
Oh,
number
it's
of
the iteration index.
the reiteration,
Yeah,
okay.
yeah, iteration T.
Yes,
Because you start with some very small initial solution that you solve this exponentially large linear system. And then you build on by iterating and add the
yeah,
rest.
understand. So then I think this tomography problem is you are solving a one snapshot problem.
Tomography is a one snapshot problem in the sense that as in any statistical inference problem, we assume the target, which is the ground truth routing topology, that one is fixed during the inference.
Okay,
Yeah.
okay. Why I'm asking you these things, I'm thinking about like the scaling of the NFV problem. Sometimes we solve it as the online optimization as a on the fly.
Okay.
So then in your when you're dealing with that capacity constraint, it seems like we are combining these topology inference with the optimization of the scaling problem. And then I'm thinking, how can we do the scaling, the online scaling of these NFV instances? We at the same time we do this topology inference.
By scaling, you mean you are
Like
going
the-
to fan out, duplicate your instance and.
Yes, like the how many resource allocation, number of instances.
Oh, okay. So you are saying that your decision, your fan out, is going to change, effectively change the routing topology. Exactly.
Yes.
Okay, yeah. And then in that case, I think the time scale of that scaling, VM scaling, sorry, not VM, BNF scaling
Yeah, understand. Yeah.
makes a difference.
Okay.
Because as in any statistical, it actually doesn't look statistical, but there is the input comes from statistical inference parameter estimation, right? Basically,
Yes,
calculates. For any statistical inference problem, you need to sort of give it enough time for the law of large numbers to kick in.
Okay.
To be able to say anything reasonable about the results.
Okay.
So in that case, it is true that that means there is a limitation about how fast the ground truth can change. If the ground truth changes too fast, you cannot keep up. If the ground truth is not changing by itself and you are inducing the changes
Okay,
by
okay.
adapting your network configuration, then there's a limitation about how fast you can do
Okay,
the
okay.
adaptation. Doesn't
Okay,
make
that makes sense. Yes, thank you, thank you.
So if you're talking about the data flow, the demand keeps changing, that's going to be noise. Basically, that's going to say if your routing is not changing, but the background flow changes. That means the topology, routing topology is fixed, but the link metrics will change. That link metrics will change. That's going to, I think, cause noise, but may not be disruptive. We haven't addressed that scenario to be specific. Just thinking loud, I think that's still a hopeful problem.
Okay.
But if topology changes too fast, then I think it's on.
Sure, yes, understand. Thank you,
Thank
thank you.
Yeah, about this NFA, I was thinking like those actually correlated, right? So the underlying NFA will change will be portable. For example, you derive an overlay network solutions, right? You direct those demands about those tunnels. And then the NFA system may be scaling due to the traffic demands you just scheduled, right? So the underlying network may just, the NFN network may actually be changed because of the solution of your scheduler. Right, so it's not like the change was independent of the schedule, because why we need to scale is because we have like a hotspot and you have large demands there. So six is like correlated problems.
First part of the routing.
Yeah,
I'm talking about the first part of the route or the
the routing part,
The routing part.
yeah,
So the question, okay, so in short, this one is a two-step.
yeah.
One-shot solution. When you are doing the inference, you are not doing routing. You're doing the routing, you already get the results from inference. But if you enlarge the time horizon, then you want to do it over and over again, maybe because your demands are changing. Then the easy way is to just repeatedly do this optimization. But if you want to do further optimization, let's say, can I leverage some of my passive measurements from snippet data packets to reduce the number of probes I have to send? Then I think that's going to trigger what I believe is an open problem. That gives you further optimization essentially to overlap sort of how you collect the measurements.
Yeah.
Okay. To my knowledge, I haven't seen any study. on that. Thank you.
Right, so let's, thanks, speaker.
Thank you for that.